Hello everyone and welcome to section 11.3 from chapter 11, where we're going to be discussing chemical agents for microbial control. So we hope to have learning outcomes of naming a desirable characteristic of chemical control agents, discussing several different halogen agents and their uses in microbial control, listing the advantages and disadvantages of our use of phenolic compounds as control agents, and explaining the mode of action of alcohols and their limitations as effective antimicrobials, pinpointing the most appropriate application for hydrogen peroxide agents, defining the term surfactant and explain this antimicrobial's mode of action, identifying examples of some heavy metal control agents and their most common applications, discussing the advantages and disadvantages of aldehyde agents in microbial control, and lastly, identifying applications for ethylene oxide sterilization. So we're going to start off just discussing what forms of antimicrobial chemicals are available. So they could be in a solid, liquid, or gaseous state, or for convenience, we can have a solid or gaseous antimicrobial chemical that can be dissolved in water, alcohol, or sometimes a mixture of the two. So when we have an aqueous solution, that means that they are in solution with just pure water as the solvent. Whereas if they are in a tincture, they are usually in pure alcohol, or it could be a combination of water and alcohol mixed together. So this next chart is going to basically be a list of the most commonly used agents within the healthcare field. So we're going to go through and discuss each of these in more detail. Just wanted to give you some examples here on the side. What I think would be helpful for your exam is to create a concept map. I said this kind of in class, but in the center I would put chemical agents in healthcare, and then branch it into more of what the target microbes would be. So I would have one branch, and I can kind of draw this out so you can get a better idea. So if here is, I'm going to abbreviate my chemical agents in healthcare. Okay, that's my center. What I would do is branch off and write sporicidal. Mouse. I used to have a pen, but I lost the pen to write, so I have to use the mouse now. So sporicidal, and then we would branch off and make chlorine, one of the agents there. Another one that we are going to discuss is going to be hydrogen peroxide. So I'm just going to put H2O2, and then another one we'll discuss is going to be glutaraldehyde, and so forth. So you kind of get the idea. So then I would make another one here that would list some, I'm just going to abbreviate, bacteria, viruses, and fungi, and you would put your phenolics over here. Okay, so I think you kind of get the point. So that way you get a nice overview of what all of these chemical agents are and how they're related to killing off certain microbes. So let's talk about chlorine first. This is sporicidal, although it works slowly. This is going to basically kill off the most resistant of microbes, and its toxicity is in its gaseous form. So you don't want that to be present in your surrounding. You want it within a solution, but when it is in solution, you want to make sure you don't get it onto your skin, as it can be irritating. They are inactivated by organics, and they are unstable if it is in sunlight, so keep it out of there. And then we have our phenolics, and phenolics are used in, if you were to compare it to something that you probably use in your household, they are in Lysol, so that's the active ingredient there, and their target microbe is some bacteria, viruses, and fungi. You don't want to get this on your skin, as it can be absorbed and it could cause some damage to our central nervous system. It does have poor solubility and it can be expensive. Next, we have chlorhexidine, and this kills off most bacteria, some viruses, and fungi. It has low toxicity, so this is good for us. It's also fast-acting, mild, and has some residual effects. So an example of this would be using it within our mouthwash. Next, we have alcohols. We have a couple different ones that are chemical agents for us. They're going to kill most bacteria, viruses, and fungi. It can be toxic if we ingest it, and a mild irritant, and it can dry out our skin. Comments here would be that it is also flammable and fast-acting. Hydrogen peroxide, we want to talk about it in its stabilized form. It is sporicidal, so kills off the most resistant type of bacteria. It can be toxic to the eyes or if it is ingested. It does have good stability. As we said, we're discussing the stabilized version here, and it works well in organic matter. So any part of our body or, anything that has that carbon compound is going to be organic matter. So anything that comes into contact with that. Okay, and then we have our quaternary ammonium compounds. Now this is going to kill some bactericidal, virucidal, and fungicidal activity. So it'll stop that. Remember, when we have that cidal suffix, we are referring to killing those microorganisms. It can be irritating to our mucous membrane, so that would be the lining of our respiratory, digestive systems, most likely. We also have mucous membranes in our uroreproductive system, just so you're aware. And it can be poisonous if it is taken internally. The weak solutions can support microbial growth, and it is easily inactivated. So here's an example of some disinfectant cleaners that we can use within our home or within the healthcare clinics. Next, we have soaps. So these are a very small, narrow spectrum of microbes that it's going to kill off. It only really targets very sensitive species. It's non-toxic, few, if any, toxic effects. We really just use it to remove soil, oil, or debris, or reduce the microbial load that we have on either an inanimate object or animate object. Next, we have silver nitrate. This is going to be bactericidal. This is what the silver nitrate sticks look like. And you put a solution on there, and then it will work. It usually is used to cauterize. It can be toxic and irritating, and it also can discolor the skin. Next, we have glutaraldehyde. This is commonly used, and it is a sporicidal again. It can irritate our skin and become toxic if absorbed. It's not inactivated by organic matter and unstable. And lastly, we have ethylene oxide gas. This is also sporicidal. It can be very dangerous to our eyes, lungs, and it can be a carcinogenic, meaning it can cause cancer. So in its pure state, it could be explosive. It has good penetration, and materials must be aerated. So we have a image down here of a chamber that has this ethylene gas in order to kill off the microbes in a controlled environment. Okay, next we want to talk about some desirable qualities of a germicide. Now keep in mind that there is no perfect germicide out there, but these are things that we look for, and we want to outweigh the advantages and disadvantages. So first, we want to look for rapid action in low concentrations. We also want it to have solubility in water or alcohols and have that long-term stability within it. Broad spectrum microbial action without toxicity to human or animal tissues. By saying broad spectrum, we are basically saying that we want it to be able to kill many microbes, many different types of microbes, instead of a specific genus or species. And then we have penetration of inanimate surfaces to sustain a cumulative or persistent action, resistance to becoming inactivated by organic matter. Like we said in class, if a chemical agent comes into contact with organic matter, sometimes it can become inactivated and not work anymore. And then we have non-coercive or non-staining properties, and sanitizing the deodorizing properties. And lastly, affordability and ready availability. So we don't want a germicide if it is going to be extremely expensive and nobody can afford to purchase and use it, or if it's really difficult to manufacture and put out there, then it won't be available for people to purchase and use. So we have 3 different levels of germicides. Our high level are basically going to be those chemical agents that were targeting microbes that were sporicidal. So they're able to kill endospores, and they can cause sterilization if they are used properly, meaning the proper concentration, left the proper amount of time. So critical items that we're going to use these high-level germicides for are going to be items that are not sterilization. They cannot have heat sterilization. So that would be like catheters, heart-lung equipment, and implants. Next, we have our intermediate level germicides. So these are used to kill fungal but not bacterial spores, resistant pathogens such as tubercle bacillus and viruses. So if you look here, here's our bacterial endospores. It's basically kind of covering all of the microbes underneath that area. So we use this to disinfect our semi-critical items like respiratory equipment and thermometers. And lastly, we have our low-level germicides, and they are only able to get rid of vegetative bacteria, fungal cells, and some viruses. So smaller spectrum over here, going down from the Staphylococcus and the Pseudomonas. And so they're used to clean more non-critical items like electrodes, straps, and furniture that touches skin, but not our mucous membranes. So this is a little bit of review from section 2. What are the modes of action that these germicides are trying to target? They're pretty much the same things that our physical agents were trying to target. The proteins, nucleic acids like DNA and RNA, cell wall, or the cell or plasmic or cytoplasmic membrane. And so now what we're going to do is discuss these germicides based on their chemical groups. So our first chemical group, and just to quickly mention, this is another one in which I would create a concept map for from this point on. So you would have your chemical agents in the center, and then if you want, you could put based on chemical groups. I would circle that and then branch off into each of these groups. So for example, we're first going to talk about halogens, and then I think we move into phenols and so forth. So you can go ahead and show branching, like fluorine is a halogen, bromine is a halogen, and chlorine and iodine. Okay. So let's talk about halogens. First of all, let me discuss what a halogen is, since it's been a while if you've been in chemistry, but these are going to be our non-metallic elements, and they are microbicidal and also sporicidal. So it kind of depends on which ones you're using and how you're using them. We have fluorine and bromine, but we are not going to discuss them in detail. Instead, we're going to focus on chlorine and iodine. And these are such great chemical agents that they are used as active ingredients in about 1/3 of all of our antimicrobial chemicals. So first we'll discuss chlorine. And chlorine has a couple different forms, or we use it in a couple different forms. First, we have our liquid or gaseous chlorine, and that is going to help us to disinfect water for the most part. Next we have our hypochlorites. And these are going to do a lot of things for us. You probably know it as our household bleach, which is a weaker type of hypochlorite. It is sodium chloride. And what that does is it denatures the enzymes within the microbes, which inhibits or halts the metabolic reactions within the cell. And of course, if it can't create those chemical reactions within the cell's not going to be able to thrive and it will die. You might also recognize that it is used to treat swimming pools, and it can also treat open wounds as well. We'll talk more about that in a minute. And I've decided to, in this section 3, to cut out some material just so you have a lot of memorization to do. So I'm actually going to cut out chloramines. We will not be talking about them. But just so you're aware, I have to add this in. If you don't have clean water, this could be an alternative to water treatment. As a whole, chlorine is going to help us to kill bacteria, endospores, fungi, and viruses. So we got kind of the whole spectrum of what we can kill off. It is less effective if it is exposed to light. We talked about those UV rays that affect it in those previous charts. Or also if we have an alkaline or basic pH, or if we have excess organic matter present, then it kind of inactivates it. So we talked a little bit about those hypochlorites. We have a broad spectrum here of where we can use it. And like I said, we are not going to discuss these chloramides. And a lot of people are seeing through research that this could be quite toxic. So that's why we don't really utilize it anymore. I mean, it's in some of our tap water, but they're trying to pass some bills to stop putting this within the water. All right, next we have iodine, or a couple different compounds of iodine. So we have our aqueous iodine, which actually, before we talk about aqueous iodine, let's talk about free iodine. Free iodine is going to be able to penetrate cells and disrupt the metabolic processes. So once again, those chemical reactions are able to take place in the cell and kills off the cell. Now, when we have iodine in an aqueous form, so put into a water solution, then it is going to be able to be used as a topical antiseptic. We can use this before surgery on the skin, and occasionally it is used to treat burned or infected skin. So right here you're seeing a wound here that has been infected, and over here you just see before surgery they've kind of placed that over the skin to kill off any microbes. If we have an iodine tincture, which really isn't used anymore, that means we have iodine dissolved in either pure alcohol form, or they do a mixture of water and alcohol. Like I said, it's a little bit more toxic in this type of format, so not really used anymore, but it was used for skin antisepsis, but it is not safe anymore. Next, let's talk about iodine tablets. So this is used for disinfecting water in emergency cases. You can't have too much iodine within your body because it can be toxic or cause some type of pathology like hyper or hypothyroidism. So you don't want to use this all the time. And then lastly, we have iodophores. And this is going to be basically a mixture of iodine and alcohol. And what it does by mixing it with an alcohol is it allows a slow release of free iodine. So it's used to also prepare before surgery, either on skin or mucous membranes. A specific type that is used in healthcare is usually betadine, and this is going to help with patients that could possibly suffer from pressure sores or decubitus ulcers. If they start to see that that skin is becoming moist, not getting circulation, they can put some of the betadine on there, and it kind of helps to dry it up a little bit before anything takes place. All right, so now we're going to branch off into our phenols, and it is the first major antimicrobial chemical used. It was actually derived from a distillation of coal tar, if you can believe that. But we see that it has a lot of toxic and irritating side effects, so it's not used so much in this phenol composition, but instead we use different compounds related to the phenol. So here you're going to see some cresol, and we'll talk about some chlorophene and hexachlorophene as well. So more the phenolics are going to be used in healthcare. They're going to destroy vegetative bacteria, fungi, and most viruses. So it's kind of more of a disinfectant rather than sterilization at that point. It's able to act in the presence of organic matter and has this detergent type of action, but it is too toxic to use as antiseptics. So examples of phenolics would be cresols that we saw beforehand. It is a derivative from a phenolic, and we combine this with soap in order to use it in a healthcare field. Next, we have our bisphenol, and this is usually used as a aerosol spray and cleansing soaps. It is also a version of this. You may have heard of BPA being used in plastics and how that is toxic to us and can cause things like cancer. But they have since been removing this from plastics. You'll see it a lot on like baby bottles or sippy cups, but also Tupperwares or other plastic items we use in our home. Next, we have triclosan, and this is something that they're fighting the FDA for to take out of a lot of our disinfectants, but mostly our soaps that we use, because they're also seeing that as we're using this, we are starting to create more resistant strains of bacteria, since it's kind of overcoming this chemical to kill them off. And it could be used as both a disinfectant and antiseptic. We find this in a ton of different products like kitty litter. We also talked about it being in soaps and also in certain toothpaste, but I think most toothpastes have taken it out at this point. Next, we have chlorhexidine. We are going to use this for hand scrubbing and surgical prep, and also on our other medical devices. Just in case you're wondering, we got both of these terms here, chlorhexidine. So that is a combination of a chlorine molecule and also two phenolic rings. So that's kind of why it's in this category of phenolics. Next, we have our alcohols. So our alcohols, the ones we'll be discussing are really ethyl and isopropyl alcohol. They're both used for microbial growth and we use for microbial control, and they are going to be the most efficient at around 70%. Some things about both of these types of alcohols is that they're both going to be microbicidal, and we'll see that they're more effective for enveloped viruses versus our non-enveloped viruses, which makes sense because the non-enveloped ones are more resistant. And a little bit of a difference between the two is that isopropyl alcohol is going to be more effective and less expensive. So it's usually the case that you are going to choose isopropyl over ethyl alcohol. And then if the alcohol is evaporating quickly, then it does limit the effectiveness of the alcohol. So let's go on and talk about these individually. Our ethyl alcohol is going to be, we said most effective at 70%, but we can go up to 75% to make it more effective. We use it for skin degerming and disinfection of some types of medical equipment. And like we said, evaporation is going to limit the effectiveness of this. With our isopropyl alcohol, same comments here that we've already said. The only thing we need to mention is that the vapors can affect the nervous system. So next we have hydrogen peroxide. I apologize that for some of these compounds, I don't know, I couldn't get rid of this. It's showing arrows going down. That's basically saying this should be a subscript. So H2O2 is our compound of hydrogen peroxide. So what's great about hydrogen peroxide is that it is going to have germicidal effects that release a toxic and reactive oxygen. So maybe you've noticed if you put hydrogen peroxide on a wound that it starts to bubble. So what it's happening is as it makes contact with organic matter, our skin, it is going to rapidly be exposed to an enzyme called catalase, which is released by our tissues or cells within our wound, and that is going to cause our hydrogen peroxide, H2O2, to turn into water, H2O, and oxygen. That would be the remaining O that was taken out. And so that's why you get that bubbling effect, right? So we could imagine that hydrogen peroxide would be the most effective in treating infections by anaerobic bacteria because they have a setup where oxygen is very toxic to them, very lethal to them. So hydrogen peroxide is one of those golden standards of a germicide because it can kill off a full spectrum. It's bactericidal, virucidal, fungicidal, and sporicidal at high concentrations, with not too many, or not affecting our bodies. So we can use it as an antiseptic on our skin and to cleanse our wound, and also for bed sore care and also within our mouthwashes. It can also serve as a disinfectant for things like our soft contacts or contact lenses, surgical implants, plastic equipment, utensils, bedding, and room interiors. You could tell it's later at night. I've taught all day, so I'm not able to speak anymore. I apologize. So the next thing we need to mention is that we can also use hydrogen peroxide for sterilization of our delicate reusable instruments. And the reason we want to do this is because these instruments are very expensive, in the tens of thousands of dollars. And so we can put it into something known as a low temperature sterilizing cabinet that you see pictured here to the right. And it is going to contain a liquid chemical sterilant. So in this case, it is our hydrogen peroxide, about 35% there, and also peracetic acid, that's also 35%. And it's able to sterilize the instrument without damaging it. That would take place if we tried to do sterilization using heat. If we use vaporized hydrogen peroxide, we are able to do things like sterilize our small industrial items, or we could do a larger enclosed space. So we would fill a room with hydrogen peroxide vapors at a high concentration, and that would be enough in order to kill off endospores, so another wide spectrum. And then lastly, we have ozone, or O3, and we see that it has similar effects to hydrogen peroxide. It's able to be used to disinfect the air, water, industrial air conditioners, and also cooling towers. So this brings us to detergents. If our detergent has polar molecules on it, it acts as a surfactant. And on these detergents, you'll see that they have a positive charge to them. So this is why we kind of see the plus up over here and also over here. The reason that this is such a good chemical agent is because it has this positive charge to it. Now, we've discussed that bacterial proteins on its surface have negative charge to them. So it is drawn to that negatively charged bacteria. And when it's drawn to it, it is going to bind to the plasma membrane and basically just get rid of the selective permeable membrane that's created by the plasma membrane. And of course, if we ruin that permeability, then it is going to basically cause cell death. And also on the detergent, we will have some uncharged hydrocarbon chains, and that too will disrupt the cytoplasmic membrane. We won't go into all the details there, but basically the end-all picture here is that these detergents and surfactants are going to destroy the cytoplasmic membrane, which doesn't allow it to be selectively permeable anymore, leading to cell death. We will see that there is a variety of effects, and our activity can be reduced by the presence of organic matter. We'll also see that they function best in alkaline solutions as well, or a basic type of solution. So the ones that are used quite a bit are quaternary ammonium compounds, or they're also nicknamed quats. They could serve as disinfectants when we mix them with a cleaning agent to sanitize a variety of objects and surfaces, cleaning restaurant eating utensils, food processing equipment, dairy equipment, and clothing. Or we can even use them when we mix them with cleaning agents to disinfect and sanitize floors, furniture, equipment surfaces, and also restrooms. We do have preservatives for ophthalmic solutions and also cosmetics too. So next, let's talk about some soaps. These are going to be weak microbicides. Sometimes they're so weak that they are microstatic. Pseudomonas is going to be very resistant to soap, so we have even seen that they are abundantly grown within soap dishes. But what we mainly are going to use them for is to mechanically remove large amounts of surface soil, greases, and other debris that are going to contain microorganisms. And if we are able to combine it with chlorhexidine or iodine, then it is going to be more germicidal. So here is a chart showing us the effects of hand scrubbing. You can see in blue we have the non-germicidal soap versus the green, which is germicidal soap. And you can see as we move through the number of days, we are reducing the amount of bacteria that is found if we use the germicidal soap. So no surprise there. And that brings us to our heavy metal compounds. So types of heavy metal compounds would be, ones used in the past would be mercury, silver, gold, copper, arsenic, and zinc. These are not all used today. Instead, more silver and mercury are going to be the ones that are more significantly used in healthcare. And they are able to create a property that we use the term oligodynamic action. And what that means is that we just have to have a little bit, minute quantities, in order for it to be toxic to microbes. Unfortunately, we are going to have a lot of drawbacks here. to using these heavy metal compounds, such as the metal being very toxic to our bodies if it's ingested or inhaled or absorbed through our skin. Like I said, it just takes a little bit of that metal in order for it to become toxic to not only microbial cells but also to our cells. What they do in microbes is that they are going to bind to functional groups on the proteins, and that inactivates them. So metabolism isn't able to take place anymore, which causes the cell to die. So it could do the same thing in our own cells, since we too have proteins within our cell membrane. And then the other thing that is a drawback is that they are often going to cause allergic reactions. They can, in large quantities of biological fluids and wastes, neutralize their actions, and the microbes can develop resistance to these metals as well. Let's move on and talk about some applications of heavy metals. So we can create weak organic mercury tinctures. They are effective antiseptics and infection preventatives. And examples of this that you may have heard of is Thermosol and Nitromersol. These, especially Thermosol, is used as a preservative in cosmetics and also ophthalmic solutions. Thermosol is also put into vaccines in order to preserve them as well. So let's talk about some of these silver compounds too. Silver nitrate is an interesting one because it was used in the late 1800s in order to prevent gonococcal infections in the eyes of newborn infants. When they were moving through the birth canal, they were exposed to infective tissues, and so they would use the silver nitrate in order to kill off the microbes and prevent the newborn from becoming infected as well. The problem is now that a lot of the pathogens are resistant to silver nitrate, so we use more antibiotics in place of the silver nitrate. Next we have silver sulfadiazine, and they found that when you use this in the dressings of a burn victim, that it is going to more effectively prevent an infection taking place in either a second or third degree burn. And like I said, I'm going to cut out some material here, so we will cut out the rest of these silver compounds: pure silver, colloidal silver, and silver ions. So when we talk about a aldehyde, that means that we have a functional group that is a CHO, carbon, hydrogen, and oxygen attached on the terminal carbon of that compound. Now, I didn't put a compound here for you just because this isn't a chemistry course, but just wanted to maybe make that a little bit more familiar to you if you remember it from a past chemistry course. So the two aldehydes that we are going to use the most is glutaraldehyde and formaldehyde. And we're also going to talk about this orthophthalaldehyde or OPA. So with our glutaraldehyde, this is going to be a yellowish liquid. It has a mild odor to it. And what it does to our microbes is it cross-links the protein molecules on the cell surface. And when it does that, the amino acids get that alkali attached to it. And so it's not going to be able to carry out its enzyme activity properly, and that will cause the microbe to basically die. The glutaraldehyde is going to be a rapid and broad spectrum type of agent, and it's also been accepted as a sterilant. So if it's used correctly for the right period of time, it can destroy endospores. It takes about 3 hours for those endospores to die. And for other microbes like fungi and vegetative bacteria, such as Mycobacterium, it would take just a few minutes. And it also does a great job of inactivating viruses as well. And the other great thing is it still is going to work well, have its potency in the presence of organic matter. The only drawback we have with glutaraldehyde is that it is somewhat unstable. Now, formaldehyde is going to be a gas. It's sharp, it's irritating, but usually what we do is take it and put it in an aqueous solution, and we call that formalin. And that formalin is usually right around 37% solution from the formaldehyde gas. And what it does is it attaches to nucleic acids, so DNA, and also functional groups of the amino acids. When it attaches itself there, then those aren't going to be functional and basically will lead to cell death. Now, this does act more slowly than glutaraldehyde. It's also extremely toxic. It is irritating to skin and mucous membranes, and is also a carcinogen, meaning it can cause cancer. So I am around formalin all the time because it is also used to preserve and embalm the cadavers, but we are always monitoring the levels to make sure that they are at a safe level where they shouldn't be irritating to our body or causing cancer. So next we have OPA, and this is very similar to glutaraldehyde. It is less irritating. This is more of a pale blue liquid instead of the yellow like the glutaraldehyde. And they work in a similar type of mechanism as glutaraldehyde. So attaching itself to the amino acids and not allowing it to go through those processes we talked about in class, like DNA replication and transcription and so forth. What else did we want to mention here? The other thing is that it is not quite as potent as glutaraldehyde. It cannot destroy endospores. So how can we use some of these aldehydes? For glutaraldehyde, we can use it to sterilize materials that would be damaged by heat. So things like hemostats or endoscopes or kidney dialysis equipment, sometimes dental instruments as well when we use it in combination with autoclaving. Remember, that's when we increase the pressure and temperature. And then also formalin tinctures can be used to disinfect surgical instruments, or the formalin solution has applications in aquaculture to kill fish parasites and control the growth of algae and fungi. And I already mentioned that formalin is used as an embalming fluid for cadavers. So let's move on to ethyl oxide. We talked about ethyl oxide a little bit previously. Just to refresh our memory, it is a gas and it is colorless, but it is very explosive. So usually we don't want it, handled just by anybody. You want to make sure you have the proper training here. And they usually are going to combine it with a high percentage of carbon dioxide or fluorocarbon in order to make it less of that explosive type of level. So what ethyl oxide does, it is going to react with functional groups in DNA as well as in proteins. And by interacting or reacting with those DNA molecules and proteins, it's going to block DNA replication, which affects the enzyme activity of the cells, and that leads to cell death. Now, in order to use ethylene oxide, we need to use something called a chemiclave. And that is a type of chamber that is similar to an autoclave. If you go back a couple of slides, I have a picture of what that looks like. And in this chamber, you can place your items in there. And it is pretty slow. It takes about 90 minutes to 3 hours in order to sterilize the objects, whatever you put in there. So it can also cause damage to our lungs, our eyes, and mucous membranes if it's contacted directly. And this too, I can't remember if I mentioned before, it is a carcinogen as well. And here is another item that we are going to cross off. So don't worry about this chlorine dioxide. You can read about it if you're interested. So what is an application of ethylene oxide? We are going to use it to sterilize and disinfect plastic and delicate hospital instruments such as prepackaged medical devices, surgical supplies, syringes, or disposable petri dishes. And it's even been used to disinfect sugar, spices, dried foods, and drugs. Here is another part that we are going to cross off. My pen went away. Propylene oxide, don't worry too much about it. Basically, it does similar things as ethylene oxide, but it's safer to use and less toxic. Let's also get rid of these dyes. Okay, so don't worry about this slide. We're going to cross this off. And also we could cross off the acids and alkalis. But I do want to talk about these negative effects of, what did I just do? Sorry about that. These negative effects of triclosan. We mentioned this before. We are seeing in a research study that this triclosan is excreted in the urine of 75% of Americans. So we are able to also, because it's used in so many products, we are able to detect levels of this within our groundwater sources. So as you're using it, let's say you find it within your soap and you're washing your hands with the soap, then the triclosan is being washed down the drain and into rivers, wells, and our tap water. So what happens there is it's going to degrade into a dioxin-like compound when it's exposed to the sunlight, and that poses risk to our environment and our plants and our animals. It is creating more of a resistance of microbes to other chemical agents and antibiotics. So this can be very dangerous as it continues. We are using this water for our crop irrigation as well. So it could trigger an evolution of more resistant microbes, which can be within our food supply as well. So the American Medical Association is warning us not to use products that include the triclosan and banning it from, or the APHA, American Public Health Association, has banned it in non-medical applications. So there's still a lot of laws being passed for this, but at least it shouldn't be in more of our products. And then for these next couple slides, I just thought this would be something that would interest you, but I'm not holding you responsible to know this for your exam, to go through and see what kind of chemical agents you have within products that you have in your home. So we got 2 slides there. And then don't worry about this concept check, because I'm going to include some of these questions within your quiz that you should take after watching this screencast. And you will find that on Blackboard under week 5 for chapter 11. So always feel free to contact me if you have any questions, or come to tutoring on Thursdays at 3 p.m.